Hello everybody, my name is Sri Krishna from CSE AML branch 4th sem. Today I am going to discuss about transaction processing in database management systems. The concept of transaction provides a mechanism for describing logical units of database processing. Transaction processing systems are systems with large databases and hundreds of concurrent users executing database transactions. For examples, airline reservations, banking, credit card processing, online retail purchasing, stock markets, supermarkets, checkout, and many other more applications. These systems require high availability and fast response time for hundreds of concurrent users. A transaction is typically implemented by a computer program which includes database commands such as retrievals, insertions, deletions, and updates. Effective transaction management is a core function of any robust database management systems. In this presentation, we'll explore the key concepts, mechanisms, and best practices surrounding database processing to ensure the integrity and reliability of your data. Uh, the main objectives of the transaction processing is to study transaction properties, to study creation of schedule and maintaining schedule equivalence, to check whether the given schedule is serializable or not, to study protocols used for locking objects, differentiating between 2PL and strict 2PL. A transaction is a logical unit of work that must be completed in its entire entirely or not at all. Transaction ensures data consistency by providing ACID properties. ACID properties are nothing but A stands for atomicity, C stands for consistency, I stands for isolations, and D stands for durability. We will dive into each of these properties and how they are fundamental to reliable data management one by one. Acid properties of transactions. A transaction should possess several properties, often called the acid properties. The first one properties of transactions is atomicity. A transaction is an atomic unit of processing and it is either performed entirely or not. The atomicity property requires that we execute a transaction to completion. It is the responsibility of the transaction recovery subsystem of a database management system to ensure atomicity. A transaction must be an all or nothing operation, either the entire transaction completes successfully or none of it does. Second one, C, consistency preservation. A transaction should be consistency preserving, that it is must take the database from one consistent state to another. The preservation of consistency is generally considered to be the responsibility of the programmers who write the database programs or of the database management system module that enforces integrity constraints. Transactions must preserve the integrity by ensuring that data is always in a valid state as defined by business rules. Next one, isolation. Isolation property Isolation is also known as independence. A transaction should appear as though it is being executed in isolation from other transactions, even though many transactions are executed concurrently. The isolation property is enforced by the concurrency control subsystem of the database management system. If every transaction does not make its updates while write operations visible to other transactions until it is committed, one form of isolation is enforced that solves the temporary update problem and eliminates cascading rollbacks. Rollbacks. Concurrent transactions are executing independently to avoid conflicts and maintain consistency. Next one, durability. Durability is also known as permanency. If a transaction changes the database and is committed, the changes must never be lost because of any failure. Durability is the responsibility of recovery subsystem. Once a transaction has completed successfully, its effects must persist and be recoverable even in the event of system failures. Next concept, transaction isolation levels. There are four isolation level: read uncommitment, read committed, repeatable read, serializable. First one, read uncommitted. It allows transactions to read data that has been modified by other transactions that we have not yet committed. Read committed ensures that transactions can only read data that has been committed by other transactions. Third one, repeatable read. It guarantees that a transaction can only read data that was present at the start of the transaction, even if it has been modified by other committed transactions. Next one, serializable. The strictest level where transactions are executed in a serial order, eliminating all concurrency anomalies. Next concept, concurrency control mechanisms. First one, locking, restricting access to shared data to ensure isolation and prevent conflicting updates. Timestamping, assigning unique timestamps to transactions to determine the serialization order. Next one, optimization, optimistic, optimistic concurrency. It allows transactions to proceed without looking, then checking for other conflicts before committing. Next one, snapshot isolation. It provides each transaction with a consistent view of the database as of a specific point in time. Uh, Transaction recovery techniques. There are three techniques: undo, redo, compensation. The first one, undo, reversing the effects of an aborted transaction to restore the database to a consistent state. Second one, redo, reapplying the changes made by a committed transaction to ensure durability. Third one, compensation, executing compensating transactions to semantically undo the effects of a failed transaction. Logging and checkpointing, transaction logs, a sequential records of all changes made to the database used for recovery and durability. Checkpointing, periodically saving the concurrent state of the database to minimize the amount of work needed during recovery. Backup and restore, creating full database backups and using logs to restore the system to a consistent state. Distributed transaction processing, there are three phases. First phase, two-phase commit. Second one, sagas. Third one, exit transaction. Two-phase commit, a protocol that ensures all distributed participants agree to commit or abort a transaction. Next one, sagas, a sequence of local transactions that can be compensated if the overall transaction fails. Third one, XA transactions, a standard for integrating transaction managers across heterogeneous systems. Next, final conclusion and key takeaways. Reliable transactions. Effective transaction management is essential for ensuring data integrity and consistency in database systems. Concurrency control. It carefully managing concurrent access to shared data is crucial to prevent data corruption and maintain isolation. Recovery mechanisms. Robust recovery techniques such as logging and checkpointing enables databases to withstand and recover from failures. Fourth one, distributed challenges. Handling distributed transactions introduces additional complexities that require specialized protocol and coordination. This is the last one, and thank you.